Yes. So, yeah, I'm going to talk about SynopSys. That is given some first insights into SynopSys, which is a project between AVI, the German Weather Service, and the University of Bremen. And we're looking into the basically operational forecast during MOSAiC. That's the first idea, so to say, where we start, and look into the forecast reliability during that time. And yeah, therefore we use, of course, the MOSAiC data as ground truth, and we take an event-based approach, and there are basically two perspectives on that. The first one is to look into the forecast skill during events, so take, for example, a specific cyclone and see how that was forecasted, and there comes the other topic we are doing high-resolution process studies, and then we also can look into these cyclones, for example, and do contrasting cyclone events and so on. And the second approaches really look into the forecast quality and basically define events based on that, so times where the forecast was particularly good or bad. And there, of course, you can play with the forecast system, so that's where the DWD part definitely comes in, do data deny experiments or introduce additional observations from the MOSAiC campaign. And then there's this third part led by the University of Bremen, where we really want to look into the Troposphere-Stratosphere interaction, so based on the model but also on observations, and there we want to use or exploit satellite remote sensing products based on ozone data and see if we can really see the exchange processes in there as well and put this in a dynamic perspective. So for observations, of course, we take MOSAiC data from MedCity, from that stuff I'm going to show here. It's the 10-meter tower and then 10-meter height. I use 10-minute average data and evaluated around the analysis time steps of the forecast, so plus minus 30 hours to do some statistics around that. Then we use the DWD analysis, so the first step in the forecast, so to say. It's the operational forecast during MOSAiC, and we use it around 50 kilometers around the observatory, so also that we can do some statistics there. And then, of course, the forecast to do the differences, to see the errors, and most of my plots I will show the 48-hour forecast. So, and yeah, this is how one of these analysis looks, and due to time I'm concentrating here on temperature, which might be insightful but also easy in some way. It's temperature versus time during April. We see these two peaks in the middle. That's the warm air intrusion that was already a topic during other talks, and in this plot we have in green the observations from the Met Tower, in blue the analysis, and in orange the 48-hour forecast. In these black, I think you can read them, but these black labels inside are cyclone events, and the lower row, this mostly 3 digits, is the distance to polar stand. So this is basically one of these approaches to see if during times when cyclones were close by, we have a worse forecast. And these hatchings then indicate the basically interesting stuff. So in green, we see if the Met Tower observations, or the other way around, if the analysis deviates from the Met Tower observations, and we see quite a lot of periods where we have, I would say significant deviations from between the analysis and the observations, particularly during winter, which is in April, more or less the first half, so we could define this still as winter. We see that the analysis was often too warm, and we see also that there's much more variability and much faster variability in the observations than in the analysis. Then we have the warm air intrusion. It was forecasted, maybe the first one was forecasted too weak and too late, maybe. The second one was quite good, which is maybe a bit surprising. And then we have the summertime where, except for the variability, you see that around the 25th of April, where the observations again start to wiggle, but the model does not. Then it becomes better. In terms of the forecast quality relative to the analysis, which would be orange hatching, one could say it's quite good. So if we stay in the model world, the forecast is quite good. Yeah, and we can do some statistics about that, so over the whole MOSAiC period. And this is basically counting time steps where I have a hatching, so to say. And we see that during summer, we have very few deviations, so I would say it's quite good. But in winter, we see that the observations relative to the analysis are often too cold. That's what I've been talking before about. But as well, we see that the forecast also is often lower than the analysis, and that could hint that one of the problems is actually in the data assimilation. So the model tends towards colder temperature, but is initialized warmer than it was observed. Yes, and then there's another work based on work from a PhD student, not in the project, but in our group, Daniela Hittmann. She did high-resolution large eddy model simulations, also with ICON. And in parallel, we did also some limited area model studies, and they found that the variability, that's also one thing I showed before, that the variability of the surface temperature is too low. And they tracked it back to basically the sea ice model. And well, the simple sea ice model in ICON, in the operational ICON-NWP, is missing any snow cover. So it's really simple, and so therefore the heat transfer from the ice to the atmosphere is too high, and basically locks it to a too warm state. And the idea was that this basically isn't too high effective heat capacity, so to say. And with consultations from DWD, we adapted the model a bit and basically changed some things in the equations and basically reduced the heat capacity of sea ice. And in a first study with ICON-LUM, so with a limited area model with basically very fixed boundary conditions, we looked into the November time where we had 2 storms, and here we see in green the MOSAiC measurements again. In blue, it's the original ICON configuration, and in black, it's the sensitivity run with the adapted sea ice model. And we see, particularly during these storms, we are now able to really capture the MOSAiC measurements, but during other times, it's not as good. So I would say in the first part of the graph, we see some improvements, but then in the other half, especially at the end, so November 21 to 23, we see that maybe the model even got worse. So there could be some other things that influence that, clouds or something else, but well, yeah, that's something to look into in the future. Okay, so conclusions on that surface part in my talk. Cold events are not cold enough. The variability is too low, but we also have some kind of solution with the sea ice model. If we reduce the heat capacity there, we are much better able to capture these things. We also did some global runs. I don't show the plots for that, but they indicate that the model is already a bit too cold if it's less constrained. So if we do model free runs with a global model without any boundary forcing, or SST and ice forcing, of course, then it is already quite cold, and it becomes also colder, which is not a good thing. So this adaptation of the sea ice model is maybe not appropriate for climate simulations, which are also possible with ICON-NWP. And of course, then there are a lot of more things on the horizon here, data denial experiments, additional data, and other dedicated experiments. So now I want to extend this a bit vertically. These are the MOSAiC radio soundings during leg 3, basically, and we see the transition from winter into summer, basically. And well, I don't want to name all these things we see there, but already on that perspective, we have a lot of events and stuff and whatever inside of it. This is the DWD analysis, which is basically the same because the radio sounds were assimilated, and well, from that perspective, also the forecast looks quite well. Of course, it would be interesting again to see these plots with data denial experiments, which are for some parts of April in the making, so yeah, we have to wait for these results. But if we take the difference between the analysis and the forecast, then this looks like that, and there are also a lot of things inside, but I want to concentrate on one thing, and that's this warm anomaly at about 18 kilometers height, and well, that reminds us on something, at least it reminded me on something, because that's really the ozone layer, and that's exactly the time and space, so to say, where we had this little, I should not call it like that, but ozone hole over the Arctic during MOSAiC. And well, that's quite interesting, because usually on a very basic state, one would think less ozone, less absorption of UV radiation. Why do we get a warm anomaly there? The ozone is assimilated in ICON, so everything should fit basically. But yeah, still we have an additional heating there, 0.5 kelvins per day. So the question is there an issue in the radiation scheme, or is it due to the rapid ozone loss we observe? And since it's only assimilated, so it's only initialized with these ozone values, this rate of ozone loss is missing in the following days. And one other thing is that actually maybe, if it's really an issue of the radiation scheme, the issue might be solved since 2021, because ICON switched operationally from the old RTM to EC-RAD. But yeah, if we look in more detail into this problem, the forecast minus the analysis now in height versus the forecast lead time, so for time step 0, the differences are 0 because it's the analysis minus the analysis. We see that in this 18-kilometer layer, the warm anomaly is really increasing over time, so that fits to this radiative heating hypothesis. And we also see that there's a cooling above and some changes in the tropopause height, but there's no clear impact on the troposphere. But we still see that seems to be a systematic error in some way, because that's only one time step now, but it's quite representative for the whole March-April time step. So what I did then, very simple thing, I created a temperature index for this 18-kilometer area, so the whole polar cap north of 65 degrees north, and did a correlation analysis, or this regression analysis between this temperature index and the pressure for the whole column, also averaged for the whole polar cap. So very broad view on these things, basically. And we see that in some way consistent with the warming in the stratosphere, we see some pressure increases in the same region, so around 18 kilometers. And we see also strong regression or correlation that indicates lower pressure in the troposphere related to this warming, which could be related to basically a mass loss of the stratosphere and basically static things, so to say. But now the question is, of course, does that impact the synoptic situation? And that's something I have to look into more detail. But if we look at the actual differences between the analysis and forecast, we see that there are some times where we see the same error over that region. So it could be at least partially related to also stratospheric effects, although, again, that's very broad view on that. So, and also we see that when the temperature anomaly, that's the index again, is the biggest, so to say, we also see the strongest anomalies in the troposphere. So, it seems like there could be something in this. Why is it not working? To do some conclusions on that one, we have this additional radiative heating in 18 kilometers. We see something like 0.5 kelvins per day and have some indications that we have also 1 hectopascal per Kelvin, which is not much, but it's over the whole Arctic. And so it could be, if we look at specific cyclones or something like that, although I still don't know exactly how I should do that. It could be more. Yeah, it could impact the development of cyclones, and of course, on that broad scale, also the tendency of the Arctic oscillation, for example. Yeah, one just comment on that, since we have some indications that these high ozone loss events may happen more often in the future. This could be really an interesting thing. And of course, the future, we will see if EC-RAD solved the problem, and the other way around, yeah, really have to check if the rapidly changing ozone is the actual error. Yeah, conclusions of conclusions, just two very broad statements, I think, or maybe I even showed that the ocean ice snow atmosphere interface is really one critical part and something where MOSAiC definitely contributed to, yeah, to improving forecasts. And the other thing is the ozone loss during spring 2020. It's really, yeah, a valuable opportunity to study troposphere-stratosphere interactions. Thank you.
Thanks very much. Are there any questions?
So we've had sort of, I guess, a similar issue in terms of the evolution of temperature over the sea ice, as you were seeing there, and I've done some work sort of looking at, putting a more sophisticated treatment of the snow. And that, and you get a much better relationship between the 2 meter temperature or the surface temperature, for example, and the radiative forcing. But what we find is that you get really penalized by cloud errors because you've got a much more sensitive surface, and therefore if you've got cloud when you shouldn't have, and the long wave or the short wave, the incoming short wave is is erroneous, then obviously you really pay for that in the scores. It might be that from a thermodynamic perspective the surface is working quite well, but you have some erroneous cloud or something like that. So
yeah, that's a good motivation to look into clouds as well. Yeah.
Thanks very much. Running short on time, so we'll have to go